Morning, everyone. My name is Pierre Siccardi, and I work for Alkon. And today we're going to discuss about sensors for trucks. So basically, for more than a decade, what we do is developing some sensors that we attach to the truck. You've got a photo of it there. We can see there's a display to show the measured values, and then in the middle of the photo, there's a long nozzle tip that's a long metal tip that's the slump sensors, and on the left of it we have an air content sensor. So we attach all that stuff to the truck. As you can see right on the drum, there's the slump sensors and the air content sensor attached to the drum. Every time the drum is making a revolution, goes through the concrete, we measure stuff, we send it to the tablet inside the cab, does calculation, show the values to the display, and send everything to the cloud. So both the drivers and people at the plant can see all those measured values. So as I said, we can measure the slump, the air content, temperature of the concrete as well, water addition through the flow meter, and volume of concrete, for example. So the point of my presentation is to see how those kind of systems can help on every step of the production. So in the next slides, we're going to go through all those different steps of the production, from the dispatching to the construction site and the return as well. So let's begin with the dispatching. Basically, a dispatch software does the production schedule. You get your order from the different customers, you put them into the software, and then you can generate tickets and assign them to your trucks. But having sensors on trucks, it helps you having a good overview of what's happening in real time on your production, thanks to the GPS positioning, and as well, based on the sensors, you can track what is the current status of every truck. So you can know if you are in the pouring step or the washing step, and that really helps both the dispatcher and the batcher to know what's going on. And that's it for the dispatching. Now let's move to the batching. There's mostly two ways of producing concrete. First one is dry batch. You put everything into the drum, you mix for a couple of revolutions, and then you've got your concrete. The other way of doing that is wet batch. In this situation, you use a stationary mixer. And when we get to figures that compares those two methods of producing concrete, most of the time, the dry batch is less effective than the wet batch. It takes more time, it consumes more fuel, and it emits more CO2. In the end, it costs 30% more on average. We should note that those figures are for the truck only, and then it depends on where you get your electricity from for your wet batch, but basically, it consumes more. And when we look at wet batch, we all know that there's some solution that exists to measure the mixing of concrete on those stationary mixers. So we install wattmeter to monitor the power consumed by the mixer, and at some point, this value coming from the wattmeter tells us, hey, you are homogeneous enough, you can dump that into the truck and go. And thanks to those devices, and according to that study, it helps to decrease the energy consumption by 17% and the mixing duration by 32%. So that's quite substantial. So the whole idea of this, and I rewind a couple of years back in the day when I was a PhD student, could we use those sensors to replicate what we do with a wattmeter, but for a truck? So could we use those signals to say, hey, you are homogeneous enough, go off the plant and go to the construction site while still ensuring that concrete quality, because in the end, we still need to be homogeneous. So let's go to the sensors. On the left, you got crosscut of a drum. And every time drum's making a revolution, the probe goes through concrete and it records a pressure applied on the tip of the probe. See, this is the signal you see in red here. And depending on the speed, the volume, and other factors, it has a very distinctive pattern. Now, if we take a step back and we have a look at the whole load of concrete. So when you put your mixed components inside your drum, pressure suddenly increase, and after some mixing revolution, you can start to see a decrease in terms of pressure, and after a while and some water adjustment, you can really notice that those patterns, they become repeatable and repeatable. So the whole point of the project was to develop an algorithm that is able to, no matter the inputs and no matter the mix, to say to the truck driver, this is homogeneous enough, you can leave. And that led to the development of that algorithm. So this is when I was at Laval University. We studied hundreds of loads on production, and after that, when we were satisfied with our algorithm, we did specific loads with the truck dedicated to the project. We learned quite a lot about the mixing kinetics, but the first main observation was, yes, those systems that are able to track this evolution, and this is quantifiable. Then, depending on what's inside the drum, it takes a different amount of time to get homogeneous. So if you have more water, if you have less volume, it will be faster to get that homogeneity. Then, as well, when we do some retempering, when the concrete was already homogeneous, but you add something else to the drum, those systems are able to quantify again this slight variation. So that's another great tool to have. And finally, what's really important there about productivity is that when you have a look at standards, they require you to mix for at least 70 to 100 revolutions for every load. By having those data, we now know that in many situations, it doesn't require to have this 70 revolution limit. And in many other situations as well, let's say you've got a high-strength mix or whatever, it needs more than those 100 revolutions. So it really fits more what's inside the drum, and in the end, you can save some time and ensure quality using that stuff. So now our concrete is fully mixed, and we can get to the next steps of production. So after the batching plant, usually the truck goes to the washout stand or the slump stand, whatever you call it, and the drivers just adjust the right amount of water it needs to get the desired workability. What you see at the bottom is, again, a typical load of concrete. You've got the RPM in brownish color, and then the slump in red. So at the very beginning, you've got your loading and mixing, and then once the RPM goes at slow speed, you get your first slump readings. Then the truck goes on the road, and as everyone should know, slump decreases. You've got the slump loss along the transportation. And when the truck arrived on site, the driver just did a retempering to get the desired and the target workability. In this case, he added 20 gallons of water, just remix, and get a new readings from the slump probe. So you can really feel that having this kind of systems, it removes the eyeball into the production. You've got a faster and and more controllable way of doing your workability adjustment, as well as when the truck arrives on site or goes out of the targets, you've got some alerts that goes to the batching plant. And finally, you remove all of these big blind spots that you have right in the middle, because usually you get, maybe if you're lucky, one slump, manual slump at plant, one at site, but what's happening in between, you don't know. So again, more control, more robustness into the system, and that in the end helps achieve a better productivity. I will now focus on the very last steps, which is the retempering. And if we look at the figures that comes from Master Builders couple of years ago, 45% of the loads, they require a retempering, so adding a bit of water to get the desired workability. And that costs a lot. You see the figure, $30, that's a couple of years ago again, so you can easily double, maybe not double that values, but quite close. Existing solution right now using systems, we have the value at site. It goes back to the batching plant and tells the batcher, hey, based on past measurements, you need to trim 3.5 gallons, for example. So it is a good thing to have that value, but still it has some drawbacks. You first need to have one truck that got to the job site to get that value with the same mix, for example. And we were thinking, and it was, again, a couple of years ago when I was a PhD student at Laval University, could we get further than that? Could we use the data a bit more to get this figure without to have this first truck and use more input as well? Because during the day, everything's changed, traffic might increase, temperature might change, moisture, aggregate moistures, they can vary as well. So could we be a bit more brighter using those data? So that led to the evaluation of could we use machine learning, AI, based on this. So the final solution would be, instead of telling the driver the target at site is, let's say, 6 inches, it would be to say, hey, you need to be at 9 now, and then leave the plant. So that led to the slump anticipation algorithm. So I will make a bit of a detour on this algorithm. What we wanted to predict was the target slump at departure. We considered different inputs in that model. You got a list of them here: load volume, concrete temperature, water cement ratio. Slump at arrival and travel time. This is stuff we have on past data because it's recorded. But then when it goes to the real-time use of that algorithm, you can get them from Google Maps, for example, and the outside temperature and humidity, you can get them for weather forecast. So I know that's not a lot of inputs. That was mainly a proof of concept that we wanted to do there. Then we can add more inputs into that, like, for example, the aggregate moisture. So we trained a couple of very known machine learning models on that. We used a couple thousands of loads. You see the results of it here. So it compares the observed slump versus the predicted slump. Both good performances, as good R squared on train and test set here. But most importantly, when you have this kind of results, what you would want to have a look at is the RMSE, so the error on that prediction. And in that case, it was 21 millimeters. When you have a look at the standards about slump, we are in the same range. So that tells us that that model is performing quite well at predicted what should be my slump at plant. Now let's move on to the construction site, and I'm glad that Jacob mentioned rheology, because we will go a bit further on that topic. So for people not familiar with the rheology, that's the study of flow behavior. So we basically compare how does the concrete move compares to the amount of force that we apply to it, basically. Water, you've got a glass of water, you bend it, it starts to flow. Concrete is a bit different. You've got a yield stress, and this is what we measure using the slump, in fact. But then as well, it got viscosity. So as many of you know, SCC, for example, it's easier to move it, but it has a higher viscosity due to amount of paste, for example. And you may wonder, why is it so critical, this rheology? Because when it comes to specialty concrete, we've seen tons of examples of segregation in the past presentation. That all comes through this rheology importance and viscosity importance. And it all matters for the productivity as well, because by having the right rheology, you don't get so much pump blockage, you don't have any issue with rebar encapsulation, so that's critical. But for now, it only stayed in the lab. It's quite difficult to measure rheology. It costs a lot. We typically use what we call a rheometer to measure rheology. This is some apparatus you don't have and you don't want to have on every job site. So we were thinking, could we measure that viscosity and that yield stress using those onboard sensors? And the next result I will present you comes from a study we did 2 years ago in Japan. And that's much more like a pet project for us. This is something we do on the side because we see not a lot of people who want to have that for commercial as a commercial feature, but still this is something we really look into because it's still interesting and still a challenge. So those two graphics, they compare the results from the ICAR rheometer to the constant measured by the truck. So we got both the yield on the left and the viscosity on the right. We've got different colors. It depends. We did different mix designs in that test. But still, if you put everything in the same series, you can see that both properties align pretty well comparing the rheometer to the truck. That's not tons of results, but still we can feel that there's some opportunity to measure rheology using those sensors. So let's wrap it up. We delivered out our concrete, and in many situations, there's still some leftover in that truck. And in fact, if you look at the figures, it's substantial. I don't know the amount of Olympic pool you can fill with that amount of concrete, but that's a lot. And when it comes to the different strategy that you can use for that leftover, you've got different ones. So if we start with the upper ones, you let it set on the ground, you crush it, you don't really use that concrete in the end. After that, you can do precast block, it's a bit better. You can dry it up, finally, and that looks the best solution to me, is to reuse that concrete. So when you go down that list, your environmental and economical benefit that you gain from those strategies, it increases, but as well the level of complexity increases as well. And again, this is something where onboard system can really help. And I'm not talking only about the one we are working on. Nathan will be presenting after me, so there's other people doing that kind of stuff here, and that's a great thing. So when I say onboard sensor, it is in general. So The last one in the list is pretty interesting because since a couple of years now, ASTM allows that reuse. And when we look at that ASTM standards, there's a couple of things you need to achieve before having the right to reuse that concrete. For example, you need to measure the volume at a quarter cubic yards as accuracy. You have a time limit, but still you can use that mixture to extend that period of time. So you are allowed to do that, but it is difficult. It is difficult for sure. But now we've got tools to do that, so that's great. I will just finish this presentation going back to the office. Having a lot of data is great, but when you can easily get lost in this. The great thing about this is most sensor suppliers, they now provide dashboards where you can use that data to track the performance of your driver, of your batcher. That way you can really spot on where you can improve the training and get things done more quickly and with a better output of your plans. And that's the end of my presentation. We went all through those steps. One last thing, that's a bit of an advertisement. For 2 years now, we've got a subcommittee on that subject. We work on a document. The purpose of that is to give all the people in the room, the owners, the concrete producers, the engineers, a document where they can refer to if they want to learn more about that and validate as well those sensors. So you can expect something that goes out of this in the coming month. So that's it. Thanks, everyone.